In this video, we discuss the second fundamental theorem of calculus. It deals with a function that is defined by a definite integral. So let's say we've got y as a function of t. Then we could actually define a function of x that starts at x equals a and ends at x equals, not, I keep saying x equals a, starts at t equals a and goes to t equals x, and gives us the area between the curve given by the y-axis and the curve given by y equals f of t. So we've got y equals 0, y equals f of t, t equals a, and t equals x. And that would be this definite integral. So it's giving us sort of that net area idea between the graph of y equals f of t, y equals 0, that's our x-axis, and the vertical lines, t equals a and t equals x. So it's a little bit confusing to students when I say t equals x sometimes. We're just saying that t equals x because we want to let that upper bound vary. So when when x equals a, if I evaluate this at a, I just get the integral from a to a of f of t. I start at a and I end at a. There is no area there, so we get 0. But if I evaluate this at t equals b, or excuse me, x equals b, I end up with the integral from t equals a to t equals b of the function. So I end up with that value, that area. And so as x continues to increase, this upper bound continues to increase. And if that function is positive, the area continues to increase, and this function f of x, which gives us the area, continues to increase. If the function y equals f of t happens to be negative, at some point we start subtracting area, and then this function starts to decrease. So there's an example of that on Desmos.com. I want to show that to you. So here's my function. F of t equals 4 plus 2t sine of t. And then the accumulation function, that's that one defined by an integral. It's the integral from from t equals a to t equals x of f of t dt. So I'm letting my a be 0. Notice that this is my accumulation function. So when I substitute in a as my upper bound, I have the integral from a to a of f of t dt. Well, that's just 0 because there's no area there yet. But if I increase my upper bound, see, when my upper bound is 3, we have the integral from 0 to 3 of the original function, and it turns out that that area is 18.22 approximately. And if we keep increasing b until we get to that x-intercept of our function, we see that our maximum, we have a local maximum in that accumulation function. That area is approximately 20, but that area starts to decrease when we start subtracting the area on this interval over here. So as our b values increases, and we're on this interval now, you can see that the total area starts to decrease. And it decreases once we get past this point of intersection, which is at 3.7. And so the area is decreasing, and then we get to that 0 point, whatever that value is, when x equals 6, the original function equals 0. And then we continue to let b increase. I don't know why it keeps scrolling down that way. And we see this. So our area under the curve is actually given by the y values on this teal graph. This is 26.655 now. And that's, again, it's giving us a net area. It's giving us this area plus this area minus this area minus this area. But we can see that when the function is negative, we're subtracting something from our area. So it gets the area under the curve decreases, or that net area decreases. And then whenever our original function, the white function here, is positive, then the teal function starts to increase. And so you can keep doing that. I've got all my b values are all between a and 15. So we've got that right there. Now, if we wanted to, we could change the value of a. And one thing I want you to notice is what happens to that x-intercept of the function capital F of x. If I let a start at 1 instead of 0, notice that the graph just shifted. I still have f of a is equal to 0. That teal graph is still equal to 0 there, because if I evaluate the integral from 1 to 1 of f of t, I still get 0. And now my b values only go from 1 to 15. So now we're starting by calculating our area from this x equals 1 value, and then we're stopping at x equals, let's say, 13.15 at this point. But we could start at a different value. We could start at a equals -5 if we wanted to. And then on that interval from -5 to that first x-intercept, or not first x-intercept, from -5 to that first x-intercept that's greater than, I said -5, from x equals 5 to that first x-intercept that's greater than 5, all of the area is negative, right? Or all of it, the area is always non-negative, I'm sorry, area is always positive, but it's all below the x-axis. So the accumulation function is only going to give us negative values until we get to that x-intercept. But then, so we only have negative values there. But then once we get to that x-intercept of the original white graph, we start adding area. And it starts to increase. I just think it's kind of cool. It's easier to see when everything, a starts at 0. But the principle is the same. You take the area above the curve, and you start subtracting area below, add the area above, subtract the area below. And this capital F of x is keeping track of how much area we've added and subtracted. And it's giving us that net area value, starting at x equals 0 and ending at x equals whatever this is. I said x, but it's really t. The original function f, this white function, is a function of t, and we're integrating from t equals a to t equals x, and then we're letting x vary. So if we wanted to, we could just let it do that over and over again. And you see how that works. I've only let b go from 0 to 15, so it doesn't continue to graph it, but it could if we wanted it to. You might wonder, okay, how is the rate of change of this function, this teal function, related to the original function here? Well, it turns out that that rate of change is equal to the integrand. So this is actually one of the antiderivatives, one way to write the antiderivative of little f of x. So let's show that on paper. And this is the second fundamental theorem of calculus, as stated in our book. Our book is the Larson Calculus text, 10th edition. At least that's the one that was given to me at TCC relatively recently. It says, if f is continuous, lowercase f is continuous, on an open interval I, and that open interval contains that lower bound of integration, then the derivative with respect to x of the integral from a to x of f of t dt is just f of x. So in other words, capital F of x equals the integral from a to x of f of t dt. is an antiderivative of lowercase f. Because if I take the derivative of this, that's this, we get little f back. All right, so that's what it says. Now we might want to prove it. It's actually relatively straightforward. We just do a lot of calculations, actually. Say, let's let f of x equal that integral. Then f prime is is the limit as delta x approaches 0 of capital F at x plus delta x minus capital F at x, all divided by delta x. And both of those are integrals. So this is the integral from a to x plus delta x. And this is the integral from a to x. And we're dividing by delta x. So there's my vertical line, x equals a, that's where we're starting. And then here's x plus delta x. And here's x. I'll just say t equals x. This is the t-axis. Well, the integral from a to x plus delta x gives us this area. And then we're subtracting the area from 0 to x, or excuse me, a to x, so that we're subtracting this area. So then what is left? I think we get the area from x to t equals x to t equals x plus delta x, right? Now, it might be a little bit hard to see at first, but that's actually the average value of f on the interval from x to x plus delta x. Now remember what our mean value theorem for integrals said. It said, if I take the interval from a to, or the integral of f from x equals a to x equals b, and I divide by b minus a, that's equal to f of c, which is called the average value of f. It's the average height. We take the area under the curve, we divide by the length to get the average height of the function over that interval. Now, the mean value theorem for integrals says if the function f, that integrand, is continuous on the interval from a to b, there is some x value on that interval from a to b, such that the integral itself is equal to the average value times that b minus a, and that function is achieving that average value at a particular value of x on the interval. So when I see this, I'm thinking, okay, by the mean value theorem for integrals, there exists an x value, well, how do I say it? A t value, right? I feel like we're using the x's for something else already. I'll call that an x star in the interval from x to x plus delta x, such that the integral from x to x plus delta x of f of t dt equals f evaluated at that x star times b minus a. So we have x plus delta x minus x. So that's going to be equal to f of x star times delta x. So what we get is f prime of x equals the limit as delta x goes to 0 of f at x star, so that's the average value on that interval, times delta x divided by delta x. It's a 0 over 0 indeterminate form as long as delta x is, or if we substitute delta x equals 0, but delta x is never 0. We're just getting infinitely close to 0. So these guys actually reduce, and you just end up with f at x star. And you might say to yourself, well, what is x star? Well, we know that x star is between x and x plus delta x, right? As delta x approaches 0 from the right, we have x is between, or x star is between x and x. The only way that's true is if x star approaches x. So f prime of x equals f of x. I think I did a little bit of hand waving there at the end. And maybe this shouldn't be an x star. Is that right? Yeah, the limit as delta x approaches 0 of this expression is f of x star, and as delta x approaches 0, x star approaches x, so this should be f of x. Okay, so f prime of x is equal to is the original function, the integrand. So I think we proved it. The derivative of this accumulation function is this function right here. And I think that makes sense. I think that makes a lot of sense. All right. Now, another way that you can prove it if you believe that f has an antiderivative, and it's kind of like a very, very basic thing. It looks a little circular. We've got the integral from a to x of f of t dt. We say, provided little f has an antiderivative, we would evaluate that antiderivative, substitute t equals a, and substitute t equals x, and subtract. Should be a t, sorry. The antiderivative of little f of t is big F of t. Then you replace t with x, that's our upper limit. And then you replace t with a, that's our lower limit. The derivative of capital F of x with respect to x is capital F prime. The derivative of f of a is 0 because f of a is just a constant. But since f of t was an antiderivative of f of t, this is just f of x, lowercase f of x. So the derivative of this is equal to this. You can think of it as taking the derivative of an antiderivative to get the original function back, but the variable changes. The variable that you have here has to be that variable there. And this is, of course, assuming we're differentiating with respect to x, because this is actually a function of x. When we integrate with respect to t, we replace the t with x, we replace the t with a, and then we subtract. This is a function of x when you're done. And then we differentiate with respect to x, and we get that. Okay, I don't know if that was a great proof, but we did it. I think we justified it, at least well enough for me. And now we can apply that formula from the second part of the fundamental theorem to compute some derivatives. So, well, let's say we're given f of x equals the integral from 0 to x of 4 plus 2t sine of t. Well, by the second part of the fundamental theorem, since the upper bound is x and the lower bound is a constant, we're just going to apply it. it just says, this is an antiderivative of this function. The derivative of the antiderivative is the function inside, but you want to make sure you replace those t's with x's. So that's that. Now, if you have, instead of an x inside that function, maybe you have, let's say, an x cubed inside. Now, when you take the derivative, you have to use the chain rule. You say, what's the derivative of the outside function? Well, the derivative of this integral from 0 to f of x of this function of t dt is going to give me the integrand but then we evaluate it at the inside function. And then we multiply by the derivative of the inside by the chain rule. And the derivative of the inside is 3x squared. You can distribute. 3x squared times 4 is 12x squared. 3x squared times 2x cubed is 6x to the 5th. So we have that right there. And then if someone asks you to compute the derivative with respect to x of the integral from, let's say, cosine of x to, let's say, x cubed of 1 divided by, let's say, t squared plus 4. I'd say, how am I going to do that? Well, I've got a function of x as my lower bound and a function of x as my upper bound, so I might want to rewrite this. This function is well-defined for all t values from -infinity to infinity. So if we want to, rather than integrating from cosine of x to x cubed, we could integrate from cosine of x to a number, and then add the integral from that number to x cubed. I'll just pick 0 because this is well-defined at t equals 0. And then for this one, I need to have this cosine of x as my upper bound. So I can use one of my properties. I can make the cosine the upper bound if we switch these and multiply by -1. You could put that -1 inside the integrand if you prefer. And now you'll use the chain rule to compute the derivative of this and this. This is your inside function this time, and this is your inside function this time. Derivative of the sum is the sum of the derivatives. So you say, well, what's the derivative of this piece? What's the derivative of the outside, which is -1 divided by that function squared plus 4. So it's the integrand evaluated at the inside, which is cosine of x, times the derivative of the inside. The derivative of cosine is negative sine of x. I'll write that as itself over 1, and then we'll multiply straight across. Then here we take the derivative of the outside again. The derivative of an integral from 0 to a function of x is that integrand evaluated at the function of x. So we put the inside function back inside, and then we multiply by the derivative of the inside. The derivative of x cubed is 3x squared. And then if we simplify, the negative times the negative gives us a positive. We have cosine squared x plus 4 in that denominator. We have 3x squared here. X cubed squared, we multiply the exponents, it's x to the 6th plus 4. And that would be our final answer. If you're saying, how do I do that in general? Let's say f of x is the integral from a to lowercase g of x of f of t dt. Then whenever we compute the antiderivative, or excuse me, the derivative, sorry, the derivative of this function is the derivative of the outside. So that's going to be the integrand evaluated at the inside function. So you put that inside times the derivative of the inside by the chain rule. So you can write this down and use it if you are not so comfortable thinking about using the chain rule in something that looks like this or something that looks like that. But this is just sort of a general version of the same thing. The derivative of this integral function is the integrand evaluated at that function times the derivative of the inside.